Okay, hey guys, I'm back with the Circuit Hadron video podcast. This episode is going to be on how to read quantum numbers. So right here I have a table of byrons, and each of these is a quantum number right here, and I'm going to show you what they all mean. This I right here, as you can see, this is its Io spin. This is, uh, right here, the Q is electric charge. This is strangeness, this is charmness, and this is bottomness. And so these are the one. I'm not going to talk about this. Also, there's rest mass, and so we'll talk about that. It's lifetime too. So these are all quantum numbers, and I'm going to show you how to read them. So this is the Io spin. Okay, spin can be thought of as a particle rotating about its own axis, even though that's not really true because they're point-like objects. But you can think of it like that if you want. So a half integer spin means it's a fermion, and an integer spin means it's a boson. So zero spin means it doesn't spin at all, and since these are byrons, which are composite particles, means that the quarks are spinning in opposite directions, so the spin balances each other out. If this was a elementary particle, such as the photon has no spin, it could be thought as the photon does not rotate at all. Because it can be displayed as a wave-like object. But anyway, so half spin means it's spinning a half. One spin means it's spinning a one. So that's spin. That's what it means, really. So half spin means fermion, means it's a constituent of matter. Zero spin means it is a boson, meaning it transmits some sort of force, usually the strong force when it comes to, especially mesons. This is the electric charge. Electric charge is pretty simple, you know. It's like you have a battery that has electric charge. Plus one electric charge means it has a positive electric charge. That's like the positive terminal in your battery. Zero electric charge, meaning it has no electric charge. That's like, say, a piece of plastic or a piece of wood. For all intents and purposes, for us in our normal lives, wood has no electric charge, unlike, say, a battery, which does. So, yeah, if you were to take a multimeter and put it into wood, you would get no voltage, whereas if you put it into a battery, you get voltage. Voltage is the exact same thing as charge, but yeah, you know, just for an example. Again, that has -1 charge, meaning it is has a negative charge. You can think of this as a negative voltage, and a positive charge is a positive voltage. And again, the higher the charge, the more power it has behind it. So that's charge. It's very simple. Then here we're getting into strangeness. Strangeness was what things that have strange quarks have strangeness. So one strange quark, for every strange quark a particle has, it adds -1 to the strangeness. So particles with no strange quarks have a 0 strangeness. This lambda, neutral lambda baron, has one strange quark, an up-down strange, thus meaning it has a strange value of -1. This sigma baron, positive sigma baron, has, again, up strange, so it has one strange quark, so it has strangeness value of -1. As you can see here, this one, the xi baron, has up strange, meaning it has two strange quarks, so it would have a strangeness value of -2, because there's two strange quarks, so -1 plus -1 is -2. So as you can see, it just goes on like that. So that's how to read strangeness. So a particle with a -1 strangeness value has one strange quark, and a particle with -2 strangeness value has two strange quarks, and a particle with 0 strangeness has 0 strange quarks. So this is charmedness, or charm. It's a quantum number, and just like strangeness, it's proportional to how many charm quarks are in the particle. 0 means there's no charm quarks in it, and for every charm quark you add 1. So as you can see, this charmed lambda has up-down charm, and since the charm quark adds +1 to the charmness value, the charm it has +1. As you can see, particles with two charm quarks in it, the strange charm, the double charmed omega baron, which has two charm quarks, has a +2 charmness value. And bottomness is a similar you read it the same way as strangeness, as in meaning that A particle with no bottom quarks has 0 bottomness. I call it bottomness. I'm not sure if is that correct. Bottomness, yes. Okay. A particle with 1 bottom quark has minus 1 bottomness, and a particle with 2 bottom quarks has minus 2 bottomness. So, the mean lifetime, which is another number, is measured in seconds, and this is simply, on average, mean, which is an average. You can look up that if you don't know what mean is, although you really should go back to 2nd grade if you don't know. But that's how long, on average, does this particle stay a particle before it decays into something else. So, as you can see, for everything except the neutron, which has 8.857 times 10 to the minus 2, mean lifetime has a really short lifetime, although for particle physics, 10 to the minus 10th is a pretty long lifetime, but for, average people, that seems like almost no time at all. And you can't even register it. That's a lot slower than you blink, or a lot faster, sorry, than you blink. So that's mean lifetime. It's very simple. Rest mass is pretty complicated, yeah, actually, more so than you would think for something like mass. But essentially, if the particle is not moving, if it doesn't have any extra potential energy or kinetic energy, what is its mass? And so these are measured in electron volts. So you can check out my mass energy equivalence and electron volt videos if you want to learn more about that. Just go to my channel and they'll be there. Anyway, that's how much mass it is. Usually things have slightly less than a giga-electron volt of mass, but so just look at the masses here. They're all about a giga-electron volt, 2 giga-electron volts, or 1,000 mega-electron volts in mass. So you can get a feel for things that are how heavy a particle is just by looking at that. Just as you get a feel for any other unit you're used to. Anyway, let's have a quiz here, okay? Cover up this column right here with your hand. Post the answer in the comment section, by the way, or in the comment section on my website. So cover up this part of the screen with your hand, and for this particle right here, okay? How many strange quarks are in it, and how many which one was it? It was I forget. Okay. Anyway, this column right here is the electric charge. This is strangeness, charmness, bottomness. So I'm going to put my mouse on the electric charge column. Scroll down to a random one. Okay, this one right here. Don't look at this column over here. Don't look at that. What's its electric charge? What does it spin? How many strange quarks? How many bottom quarks? And how many charm quarks are in this particle? Okay? And then, once you know that, put that all in the comment section. Remember the spin, the electric charge, how many strange quarks, how many charm quarks, how many bottom quarks. And then, once you find that out, what is this particle? What's its name? Okay? Don't cheat by looking at this, the left side of the screen. Okay? So just as a reminder, this column right here that I had is electric charge. The second one was strange. Third one was charmed, and the fourth one is bottomed. So if we go down to the particle again, somewhere around here, I think it was this one. Yep, so that's the quiz. This isn't the contest I've been talking about for a while, not the contest. There's really not going to be many prizes from the winner. Well, I guess the first person to get it right, please don't cheat. I mean, I have no way of knowing if you cheated or not, but please don't. Put the answer in the comment section on YouTube or on the website. First person to get it right will get mentioned in the next video. Not necessarily the next video after this one, but the next video that I make after I see your comment. So, go away, guys, and don't cheat at all by looking at the comment section or however you would cheat, because this is sort of practice that you need. Thank you for watching. I appreciate all future comments and entries into the quiz.